Soil strength is one of the most important properties within geotechnical engineering, as the strength of a soil is the maximum stress under which it can maintain before experiencing failure, which determines its ability to support structures and slopes. Constitutive models of soil are used to determine soil strength by mathematically modeling soil behavior under load, by relating the applied stresses and strains experienced within the soil. Lime treatment is a method of soil improvement to increase the peak strength of a soil by mixing in a given lime content with the natural soil present on the engineering site. The soil type, lime content, and curing time and temperatures all cause variations in the peak strength increase after lime treatment, where lime is more likely to produce a reaction with clay due to the minerals present within the clay reacting with the lime additive. The addition of lime increases bearing capacity, reduces plasticity, seasonal swells, and shrinkage, reduces moisture sensitivity, as well as improves the compactability of the soil. However, these variations are determined by the percentage of lime added to the soil. Curing time and temperature affect the peak strength of the soil as the reaction taking place within the soil occurs over a large period of time, which continuously increases the soil strength, and higher temperatures cause this reaction to take place at a faster rate. The effect of the addition of lime to the peak strength of soil is also greatly affected by both the curing time and temperature of the soil. The soil's peak strength continues to increase with time due to the long-term pozzolanic reaction which takes place due to the interaction of the soil with the lime additive. Graphs sourced from multiple research reports display that the peak strength of the soil increases towards a maximum strength. However, the increase of peak strength is lowered with larger curing periods. These graphs also showed that soil strength increases at approximately the same rate, regardless of soil type or lime content. When plotted against a logarithmic timescale, a linear equation can be produced to predict the peak strength of the soil at any given curing time. These equations shown can then be simplified to a generic equation for all soil types and lime contents, and is the function of the soil's initial strength, rate of increase, and the curing period. This equation is limited to use below 500 days curing time, as after this period the soil will not continue to gain strength at the same rate and begin to plateau, which causes this equation to become ineffective for predicting soil strength. Temperature affects the peak strength of a lime-treated soil in an exponential manner, where a small increase in temperature will result in a large increase of the soil strength. Temperature affects the soil, as higher temperatures encourage strength development as the curing process is accelerated, while lower temperatures slow the reaction between the added lime and the soil. It can be seen that lime content influences the increase of strength due to temperature, as the 6% and 9% lime soils show greater improvements than the 3% and 12% lime soils. This displays that there is an optimal lime content to produce the greatest strength increase due to changes in the curing temperature, and this optimum value lies somewhere between the 3% and 9% lime soils.
The content percentage of lime is the catalyst for changes in bearing capacity, plasticity, seasonal swell and shrinkage, moisture sensitivity, as well as improved compressibility. Based on curing testing, as well as Australian road standards for lime stabilisers in soil, 6% is seen as the optimal lime content for strength. With a higher lime content, there is a greater change in sedimentation behaviour of the soil, which effectively reduces the compressibility and increases the strength drastically, creating more of a brittle structure. On the other hand, when we consider shorter periods of lime content, smaller doses such as 2 to 4 largely increase strength and being more effective with less sedimentation. Having a smaller fabricated change in the smaller particles allowed for the plastic index to reduce. This improvement in the optimum moisture content allows for higher compressibility and better moisture sensitivity, as well as a reduced change in shrinkage and swell rates in the soil. In engineering, the most practical use of lime can be seen in the pavements and roads, both sealed and unsealed. When adding lime stabilizers, the most beneficial factors had an increased peak strength, decreased moisture susceptibility of the base and sub-base materials, as well as an increase in compressibility properties. In accordance with the Australian Roads Research Board, lime content in subgrades showed a reduce in plasticity between 1 to 3% lime content, whereas 6 to 8% had a greater effect in increasing the peak strength. Conclusively, the increase in lime increased sedimentation of soil particles, which changed the behaviour from more plastic and reduction in moisture in the lower contents to having a more drastic change in peak strength as lime content increased.
Clay soils are unfavourable foundation materials due to their affinity for water, which causes shrink and swell tendencies, high compressibility, and low strength. The low strength of these high moisture content clays, or soft clays, is a catastrophic issue for geotechnical engineers as it impacts the ability of an overlying structure to meet strength and serviceability requirements. Hence, before use in construction, clay soils need to be improved. This can be done effectively by the addition of lime. The effectiveness of lime stabilisation depends on a soil's mineralogy. Clays are layered silicates and most commonly contain the mineral groups kaolinite, illite, or montmorillonite. Upon the addition of lime, the clay's pore water becomes highly alkaline. Silicates and aluminates from the clay mineral lattices form a solution in the pore water of the soil. Over time, a cementitious precipitate will form from the reaction between this hydrous solution and the calcium ions from the lime. The cementitious product bonds the clay particles together, strengthening the soil. The ability of lime to instigate this pozzolanic reaction is what enables strength increase in soil. Pozzolanic reactions can continue for extensive periods of time, and as a result, the addition of lime can produce increasing strength gains over time, as further discussed in this presentation. The amount of lime added to a clay soil also has important effects on a soil's strength increase, as this will alter the proportion of cementitious precipitate that forms, and therefore the extent of particle bonding, which will also be further discussed. Therefore, although clays make poor building foundations, their mineralogy enables a pozzolanic reaction to occur with lime to improve the strength of the soil and make it more suitable for construction. It is imperative that soil strength be considered when determining the suitability of a soil for construction to ensure a safe and durable design. Introducing lime to reactive soils is an effective strategy to ensure otherwise low-strength soils meet design requirements. Low-strength clay soils are excellent candidates for lime stabilisation, as minerals in the clay react well with the lime to form cementitious products that bind the clay particles together, increasing strength. It has been identified that the ideal lime content to be added to a reactive soil in order to achieve optimum strength is 6%. Furthermore, as the curing time and temperature of the treated soil increase after the introduction of lime, so does the strength of the soil. The relationship between these parameters and the strength increase of soil is an important concept to model to ensure consistent predictions in a wide variety of lime stabilisation applications.